Hello, guys. Welcome to Ramta Solutions. Welcome to your grade 11 Euclidean geometry exam prep. Today, the question paper that we are looking at is from the Gauteng province. This is their November 2023 Maths Paper 2 exam. Okay, so before we proceed, it's important that we read instructions. All of the instructions are important. However, we are not going to read all of them. Okay, I'm going to read just a few. For example, instruction 3 that reads, clearly show all calculations, diagrams, graphs, etc. that you have used in determining your answers. Instruction 4, answers only will not necessarily be awarded full marks. Instruction 6, this is an exam prep of Euclidean geometry, so I have to read instruction 6 in case you will encounter a question where you have to use Pythagoras theorem. Instruction 6 reads, if necessary, round off answers to 2 decimal places unless stated otherwise. Instruction 7, answer sheets for answering question 1.1, 1.2, and 9.1 are provided at the end of the question paper. This is because Euclidean geometry is in question 9. That's why I'm reading question 7. Diagrams are not necessarily drawn to scale. Okay. Now, instruction 10, write neatly and legibly. Yes, you are aiming for your distinctions, but in your problem solving, meaning in you getting the solutions, also make sure that the presentation of your solutions is also neat and legible. Okay. So work also on improving your handwriting. So let's not waste any time and get to the questions. So we're going to question 9 and see, does it really start at question 9? Yeah, it does. Question 9, correct. All right. In the diagram below, let's see, O is the center. O is the center of the circle passing through P, Q, and R. Chords P, Q, and PR are drawn with O, Q, and OR joined. Okay. Use the diagram provided in answer sheet C to prove the theorem that states that the angle subtended by an arc at the center of the circle is double the size. Rather, is double the size of the angle subtended by the same arc at the circle. That is, prove that angle ROQ is equal to 2P. All right, let me go see this answer sheet. Answer sheet C. Do you see this? So as you can see this answer sheet, they have given you enough space. So this enough space means whatever you decide to do, make sure that, let me see, it's how many lines? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 lines. So make sure you make use of those 13 lines sufficiently. Okay? Great. Let's see, guys. Let's see. So let me go back. Right. Let's see now. 13 lines, guys. So let's see. First and first, let me copy this guy here. Come on, buddy. Let me paste him here. Okay, it's showing me flames now. I don't know why. Okay, thank you. It should be. Come on, buddy. Okay, let me do this. So it's okay. It doesn't want to be copied. I will. Okay, perfect. I've copied it. Now I can paste it. Perfect. All right, here is it. Okay, so that's exactly what you have at question at answer sheet C. So let's proceed. So now, when we answer this question, you need to start with a construction. Okay, you need to start with a construction. So in your construction, you will say draw draw PO extending to, okay, draw PO extending to, let me say S, extending to S, okay, extending to S. So let me show you what I mean. So this is PS. You see it? It has extended. Maybe let me even draw a solid line. Yeah, maybe let me draw a solid line. Okay. So this is PS. So PO, it is extending to S. All right. So I will label this part here 1, and this one here I will label it 2. Okay, I will label it 2. All right. So I don't have to say a lot because it's gonna give me small space to work on. So let me just label it. I don't have to mention that I labeled O1 and O2. So it's okay. But even if you label, it's okay. All right. So I will begin by saying something that I can see here. I can say OQ. All right. Hear me out. In fact, let me say angle Q. Oh, I don't like the size. So I'm going to say angle Q. Okay. Thank you. So I'm going to say angle Q is equal to angle O is equal to angle OPQ is equal to angle OPQ. Why? These are angles opposite equal sides. Alright? These are angles opposite equal sides. Right? So by saying so, we can therefore say angle O1 is 2 times angle OPQ. I'm using angle OPQ because at the end I have to use angle P. So why am I saying angle O1 is twice angle OPQ? This is because I had said that, or rather, this is because O1 is an exterior angle. Hear me out. O1 is an exterior angle of what? Is an exterior angle of this triangle. So, exterior angle of a triangle, right? If you recall, exterior angle of a triangle is equal to sum of interior opposite angles. All right. So we are good. All right. So we are good. Now I'm gonna go to again. I'm gonna say rather angle R is equal to angle OPR. Why is that? Again, these are angles opposite equal sides. Maybe I should tell you guys why I'm saying angles opposite equal sides. This is because OP and OR, they are radii, all right? They are radii, so they are equal. They are all originating from the center, okay? So their lengths will be the same because it's a radius, it's also a radius. The same for OQ, okay? Cool. Now proceeding, we can therefore say angle O2, right? Angle O2, checking our diagram, angle O2 is equal to the sum of angle R and angle OPR. So which we can say it's simply equal to 2 times angle OPR. Why? Exterior angle of a triangle is equal to sum of interior opposite angles, right? Good. So this is us now. We have shown that O1, angle O1 is equal to 2 times angle OPQ. Again, angle O2 is equal to 2 times angle OPR. Okay, good. So here's a thing that we know. Okay, now here's a thing that we know. Okay, here's a thing that we know. You and I, we know that we can say angle ROQ, okay, angle ROQ, okay, is equal to angle O1 plus angle O2. What is angle O1? We said it is 2 times angle OPQ. And then what is angle O2? It is 2 times angle OPR. Okay, so this is, okay, 2 times OPQ plus OPR. What is OPQ and OPR? I want you to check it out. OPQ and OPR. this angle and this angle, what are they? They are simply angle P. Okay, they are simply angle P. So we have proved this theorem that says the angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at the center. Okay, good. So we have 6 marks. Now let's proceed. Remember, guys, 1 mark that you spend in a question, or rather 1 mark in a question should be equal to 1 minute. For every mark, spend 1 minute. Okay, that will give you about 30 minutes of extra time that you can use to check whether your solutions are right or wrong. Okay, ta-da. Now let's go. So we have about 19 minutes to finish question 9. Let's see. Let's proceed. 9.2. So 9.2, in the diagram below, DF is a diameter of the circle with the center O. Okay. Chord EG, where is it? I see it. Chord EG intersects DF at HO. I see it. Such that DF is perpendicular to EG. All right. Chords EF, where is it? Chords EF and GF are drawn. All right. Angle EGF, where is it? It's this one here, is 55 degrees. 9.2.1. Determine giving reasons the size of angle D. I want you guys to follow how I answer this. Angle D, if you look at it, points D, E, F, G are concyclic. So angle D is equal to angle G, which is 55 degrees. Why am I saying this? This is because they are angles opposite equal sides. Is that so? Are they angles opposite equal sides? No, they are angles on same segment. Right? They are angles on same segment. Okay, they are angles on same segment. In other words, you see them like this. So they are angles on same segment. Okay, great. 9.2. Oh, it's A. Okay, now let's go to B. Let's go to B. This was 9.2.1a. Now B says find the value of angle O2. Find the value of angle O2. So the value of angle O2, we have angle G given as 55. You can see that O2, basically we can say it is the angle that we proved in 9.1. We can use the theorem that we proved in what? 9.1. That theorem basically says angle at center is twice the angle at circumference. So in other words, we can therefore say angle O2 is equal to 55 times 2. What is it? 110. Why is that? Angle at center. Okay. Angle at center equals 2 times angle at circumference. Okay. Equals 2 times angle at circumference. This is the theorem we proved in 9.1. Happy? Great. C. Now C, there are many ways to do C, but I will choose this one here. C, we are looking for angle E2. Do you guys see angle E2? I see it. So here is angle E2. Okay, here is angle E2. So with C, remember we are proving angle E2. So with what I have seen, right, with what I have seen, I need to remind you guys that when you look at angle E2, okay, when you look at angle E2, a part of me says, you guys recall that you can find H2 and you can also find, you're looking for E2 and you also have angle O2. Therefore, I do see, what do you see? I see exterior angle of a triangle. Okay? So let me start by saying this. Let me start by saying angle H2 is equal to 90 degrees. Why? These are angles on a straight line, isn't it? Therefore, angle E2, if you like, you can say angle E2, maybe let me not, okay, let me do this, angle E2 plus 90 degrees is equal to 110 degrees. Why is that? Because these are exterior angles. Exterior angle of a triangle is equal to the sum of interior opposite angles. In other words, O2 is equal to H2 plus E2. Therefore, angle E2 is equal to 20 degrees. Okay? E2 is equal to 20 degrees. Happy? Good. Now, proceeding, we are now going to question D. Question D, it says, look for angle E3, right? Look for angle E3. Angle E3. Now, before I proceed, I need to ask myself, E3, I also found that there are many ways of doing E3. I found about 3 methods, but I will choose the shortest and easiest. Okay, I will choose the shortest and easiest. Okay, so what I'm gonna do is this, because be careful, guys. I need E3. Do I know E1? I don't think I know E1, right? But I can say to you, before I proceed, I can say to you, angle E3, or rather angle F, right? Angle F1 is equal to angle E3. It doesn't matter. Why? These are angles opposite equal sides. Why equal sides? O1 is a radius, OF is a radius, and the radius of a circle are the same, or radii of the circle are the same. Right? Good. So we can say, totally up to you. I will write it in this way. Angle O1 plus angle, 2 times angle E3 is equal to 180 degrees. Alright? Why? Sum of angles of a triangle, or sum of interior angles of a triangle. Okay? Sum of interior angles of a triangle. What is E1? It is 110 degrees. Okay? Why am I saying 2 times E3? Because when we say sum of interior angles of a triangle, it will mean that we are saying O1 plus O2, rather E3 plus F1 plus O2. Like we had said, angle F1 is equal to angle E3. And I'm using E3 because we're looking for E3. Okay, so let me not do the long algebra. I will get straight to my questions, to my answer. Rather, 180 minus 110 will be 70. 70 divided by 2 will be 35. Therefore, angle 3 is equal to 35 degrees. Okay, angle E is equal to 35 degrees. Okay, perfect. Moving on, 9.2. 9.2, determine the length of OH. Okay, determine the length of OH if the diameter of the circle is 10 units and GE is equal to 9.4. The diameter of the circle is 10 units. Did you guys hear that? Diameter of the circle is 10 units. So we can say, what is the diameter? Because we are determining the length of OH. So it means we must be using HE and OE. So OE is equal to 5 units. Okay, OE is equal to 5 units. All right, and then if you like, though not important, diameter equals half. It equals twice radius. Rather, why am I saying half? Equals twice radius. All right, but this is not necessary. It's something we know. Okay, then I will say HE. I will say HE. Okay, I will say HE. But is it necessary to even go that route? But yeah, let me just go there. I will say HE equals, remember we have HE. It Do we have HE? Yes, because GE is 9.4. So HE will be half of 9.4, which is 4.7. HE is 4.7. Why? Perpendicular from center bisect chord. Perpendicular from center bisect chord. Bisect chord. Otherwise, others can use line from center. Okay, so perpendicular from center bisects chord. Sorry, this is 4.7 units. Okay, so now we can use Pythagoras. So when we use Pythagoras, we will say the hypotenuse of this triangle. So in triangle, OHE or E or EHO, it doesn't matter. We will say, what is this? We will say EO squared equals HE, or let me say EH equals EH squared plus OH squared. All right. Why? This is Pythagoras. All right. This is Pythagoras theorem. Okay. What is OE? It is 5 units. What is EH or HE? It is 4.7. What is OH? We do not know. So this is 25 equals this is 25 equals 4.7. Oh my. 4.7 squared is 22.09. 22.09 plus OH. Because this is Euclidean geometry, I don't have to stress, but for those who might be struggling with this, I will simply show you how I'm getting to my answers. Then you get 25 minus 2209 will be 2.91, right? It will be 2.91. Therefore, OH will be the square root of this. The square root of 2.91 will be OH. So what is this? Square root of answer. This is 1.71 units. Therefore, OH is 1.71 units. I also saw that for this question, another way that would be very short would be using your trig ratios. Okay, it would be using your trig ratios. Okay, perfect. Now, see, we were done by 22 minutes, which is 22 minutes of the video, but we started a bit later, so we are on the right track. Now, let's go to question 10. Now, let's go to question 10. Okay, let's go to question 10. Let's see what it has for us. Question 10. So, question 10. So, let's see. In the diagram below, AT is a tangent. I hope you guys noted that. AT is a tangent at T. Chords BT. Where is it? Chords BT, BV, and VC are drawn. Okay. CB, where is it? CB is extended to A, okay, such that AC, where is it? AC. Okay, such that AC is parallel to TV. Okay, cool. Then BC, okay, is equal to CV. All right. And then angle BVT, where is it? It's this one here, is equal to X. Cool. 10.1. I don't have to copy this, right? Yeah, I don't have to copy this. So 10.1, they say determine with the results 3 angles equal to X. 3 angles equal to X. I see 3 angles equal to X. Okay, so here is X, and they said these are parallel. So I will say angle B1 equal angle V2, which is equal to XY. These are alternate angles because AC is parallel to television, TV, right? Cool. Again, I can see here tan chord. So I will therefore say angle T2 is equal to angle V2, which is equal to XY. Tan chord theorem. Okay, turn chord theorem. All right. Then I can also see that BC is equal to CV. So this therefore means if they are equal, this therefore means triangle BCV is an isosceles triangle. Therefore, I can say V1, angle V1 is equal to angle B1, which is equal to XY. These are angles opposite equal sides. Okay, these are angles opposite equal sides. Okay, great. Now, 10.2, let's see. 10.2, if ATVC, where is it? If ATVC, okay, if ATVC is a parallelogram, it's a parallelogram, guys. Please note, if it's a parallelogram, I might need to copy this. If it's a parallelogram, it means opposite sides are parallel, and again, opposite sides are equal. Okay? Do you guys hear that? It means opposite sides are parallel, and also opposite sides are equal. Okay, so there are many ways of doing this. However, I'm gonna say this. I'm gonna say angle A. Where is it? Angle A. Okay, angle A is equal to, hear me out. Angle A is equal to what? Angle A is equal to angle, let me call it CVT, angle CVT. Why? These are opposite angles of a parallelogram, opposite angles of a parallelogram. Okay, opposite angles of a parallelogram. Okay, these are opposite angles of a parallelogram. So I want you to also note something I said. Angle A is equal to angle CVT. These are opposite angles of a parallelogram, right? Cool. Now, the question here wants us to prove that AT is equal to BT, right? So we know what the size is. Do we know what this size is? That's what we should also know. But good thing we know what A is, right? So how do we find maybe B3? How do we find B3? So to find B3, we can simply say angle B3, okay? Angle B3 is equal to angle CVT. Why? It is exterior angle of a cyclic quad. All right, exterior angle of a cyclic quad. Okay, exterior angle of a cyclic quad. Therefore, angle A is equal to angle B3. All right, therefore, AT will be equal to BT. Why? These are sides opposite equal angles. All right, these are sides opposite equal angles. Okay, these are sides opposite equal angles, right? We were able to prove that angle A is equal to angle B3, right? So this is us now. Okay, perfect. Moving on, 10.3. So 10.3 says determine the size of x. Determine the size of x. So guys, I want you to note something here. I didn't use any x in 10.2. So I will need to find let me see the size of x, right? The size of x. So let me see what I know. Do I know angle T2? Yes, I know angle T2, right? I know angle T2. I said it is equal to x. And then I also said angle V1 is equal to x. So I can also say, okay, hold on. Angle CVT, right? Angle CVT is equal to 2x, right? is equal to 2x. So we can therefore say, implying angle B3, this implies angle B3 is equal to 2x, right? We proved that B3 is equal to angle CVT, right? So we proved this in, it's okay to write like this. We proved this in 10.2. We proved in 10.2. Okay. Now we are good to go. Now we can proceed and say, when we proceed, we can therefore say angle A plus angle B3 plus angle T2 is equal to 180 degrees. Why? This is sum of interior angles of a triangle. Okay, sum of interior angles of a triangle. Right? What is A? We said angle A is equal to angle B3. So this is 2x. 2x. What is T2? In 10.1, we said it is equal to T2. We said it is equal to x over 180 degrees. So 5x equals 180 degrees. So this must be 36. So x equals 36 degrees. You see, we were able to finish this in less than 13 minutes. Happy? Perfect. Now, let's see now. Do you have a question 11? You see, yeah, it seems like we do. So we do have a question 11, right? Yes, we do. So we do have a question 11. So cool. Question 11. All right. So question 11, it says DE. Ooh, DE is a tangent to the larger circle at E. Where is it? Okay, cool. At E. DH is a tangent to the smaller circle at H. Okay, I see it. Chord HK. All right. Chord HK is extended to meet the larger circle at E. Okay. F and K. Where is it? F and K are points of the intersections between the circles. FK, between the circles, with FK produced to D. Okay, I see that. GK, where is it? Okay, GK is a chord of the smaller circle with FE, a chord of the larger circle. HF, what is it? HF, GH, okay, and GF. Where's GF? And GF, okay, cool, are joined. All right, interesting. Cool, we can see that. 11.1. 11.1. So 11.1 is saying to us, complete the following. Angle D3, where is it? It's this one here. Is equal to whatever plus whatever, reason being exterior angle of a triangle. Okay, if it's here, it must be this one and this one. So it'll be is equal to angle H1 plus angle E1. Okay, and that's it. That's all they want. Remember, we must be done with this in 15 minutes. 11.2, prove that DEFH is a cyclic quadrilateral. Where is it? DEFH. We must prove that it is a cyclic quadrilateral. In order for us to be able to prove that it is a cyclic quadrilateral, okay? In order for us to be able to prove that it is a cyclic quadrilateral, we need to this information here. If this angle is equal to this one, or this one is equal to this one, cool. Or if this one is equal to this one, okay? Or if this plus this are equal to, let's say this is x and this is y. Again, if x and y is equal to 180 degrees, then we can say it is a cyclic quad. Okay? We can say it is a cyclic quad. So with what I am seeing here, I can say, how would I say, I do see that F1, so hear me out. I do see that angle F1 is equal to angle E1. Where is it? It's this one here. Is equal to angle E1. Reason is tan chord theorem. Okay. Reason is tan chord theorem. Okay. All right. Interesting. Then I also see that angle F2, it's this one here. Angle F2 is equal to angle H1. Again, what's the reason? It is tan chord theorem. Okay, it is tan chord theorem. Okay, here is it. So it is tan chord. Okay, now I can see that angle HFE is equal to angle F1 plus angle F2, which is equal to angle E1 plus angle H1. So what is this? E1 plus H1. Didn't I just find it somewhere there? Yes, I did find it. What is this? We said this is D3. But hold on. Angle HFE is equal to D3. Oh, this looks like, let me show you. It looks like this information here. This is exterior angle of a cyclic quad. Okay, so therefore we will say DEFH is a cyclic quad. Okay, is a cyclic quadrilateral. Right, is a cyclic quadrilateral. But why? Because of the converse of exterior angle of cyclic quad. Alright, exterior angle of cyclic quad. So why are we using converse? We are using converse because these points, they are not really concyclic. They are not on a circle. This is why we are using a converse. Alright, had they been on a circle, we wouldn't have said converse. We would have simply said exterior angle of a cyclic quad. Okay, so this is how we proved 11.2. Happy? Great stuff. Now, let's go to 11.3. 11.3, prove that DF bisects angle HFE. Ooh, DF. Where's DF? DF bisects angle HFE. So what does that mean? That means we must prove that angle F1 is equal to angle F2. Is that possible? I don't know, but let's see. All right. So what we know is this. Angle H1 is equal to angle F1. Why? Here is it. It's because these are angles on same segment. All right. Oh, you're wondering how? Let's say this is H1 and this is F1. You see this? So this is us saying angle H1 is equal to angle F1. Right? Okay. But we said angle H1 is equal to angle F2. Right? So this we proved in 11.2. Alright? Therefore, we can conclude and say this therefore means F1 is equal to F2. Right? Therefore, if these angles are equal, we can say DF bisects angle HFE. Remember, angle HFE is this one here. So we said F1 is equal to F2. This means DF bisects them. Alright? Cool. Easy peasy. Alright. Now, 11.4. I like this one. 11.4 says, if angle K1 is equal to angle E1. Where's K1? Here is it. K1 is equal to E1. Okay? Prove that GK, where is it? Prove that GK is a tangent to a larger circle at K. So the reason this question it is tempting for you to say, with the naked eye, it's tempting to say GK is gonna be a tangent, but you don't know. What if GK just passes again, cuts another point on the circle? So now we are saying, no, let's not assume, let's show, okay, giving this information. Okay, so I want you guys to see this. So what I want you to see is this. I would like you to see this for me. I would like you to see that angle. Okay, let's do this. Angle H3. Angle H3 is equal to angle K2. Is equal to angle K2. Why? These are angles on same segment. Alright? Can you see them? These are angles on same segment. If you're wondering, I'm saying something like this, but KH2, K2. Do you see that? They are angles on same segment. Alright? Okay. I can also say that angle H4 is equal to angle K1, and this is term called theorem. Okay, and this is term called theorem. Okay, do you see that? Here is it, and K1. It is equal to term called theorem. All right, cool. Again, I can say. Remember, we proved that DEFH is a cyclic quadrilateral. This therefore would mean this angle here is equal to this angle here. So what do I mean? I mean angle H3 plus angle H4 is equal to angle, should I call it angle E1 plus E2 or angle DEF? Okay, let me call it E1 plus E2. Angle E1, okay, angle E1. Okay, it's gonna be okay if I say angle E1 plus angle E3. So cool. Angle E1 plus angle E2. What is this? It is exterior angle of a cyclic quad. Exterior angle of a cyclic quad. Alright? Of a cyclic quad. Alright? Of a cyclic quad. By now you have seen this. It is something like this. Alright? Cool. Proceeding. So now, we do have this information. Okay. We do have this information. So, remember, we want to prove that this thing is a tangent. In order for us to be able to prove that it is a tangent, let me remind you, what did we say H3 was? We said H3 was K2. And then what is H4? We said it was K1. E2, you can leave it like that. E1, you can leave it like that. And then E2, you can leave it like that. Again, you can say this. You said information given is that K1 equals E1, right? Equals E1. Therefore, as you can see, you can conclude and say angle K2 equals angle E2. Can you see that? E1 will cancel with E1. Therefore, look at this. Where is K2? Here is K2. And where is E2? Here is E2. This looks like the application of tan chord. But be careful, it is not yet tan chord. It is the converse. So therefore, we can say KF, like this GK. Is it GK? GK. Here is it. So GK. So GK is tangent. GK is tangent to the larger circle. It's tangent to the larger circle. Right. It's tangent to the larger circle at K. Why? because we are using converse of tan chord theorem. We are using converse of tan chord theorem. Okay, we are using converse of tan chord theorem. And this is how you solve these questions. Okay, this is how you solve these questions. Now, guys, with Euclidean geometry, yes, I know it's a bit complex, but do not think this is really difficult. Think of anything that you have, put it in one place and see if it's going to lead you to whatever solution that you are expecting. Okay, so this is one topic that I say when you master it, you are a problem solver. Eh? You are Dr. Phil of our problems. Okay, guys, we have come to the end of our lesson. Remember, if you would like to keep in touch with us, the links to the different social media platforms of Ramta Solutions will be given in the description. If you're watching on YouTube, it'll be given to the description of this video. And then if you're watching on TikTok, you can perhaps send us a message there. Okay. And same applies if you're looking for a tutor. You can send us a WhatsApp text or an email. Remember to visit our website www.ramtasolutions.co.za. So with that being said, it's a wrap and bye-bye.